lithium-ion batteries are the best way to power electric vehicles. But there is an alternative, aluminium air or AL-air batteries, which behave more like an engine, in that aluminium, which is the fuel, reacts with oxygen in the air to produce electric power. The technology has been around since the 1960s, but it's always been deemed too expensive to be commercialised. But now MAL Research and Development, based in Plymouth, claims to have overcome that. Well, joining me now from Plymouth is the Chairman and Chief Executive of MAL Research and Development, Trevor Jackson. Trevor, welcome to you. Is it mainly cost that's been holding back the adoption of this technology?
Yeah, it's to do with the price of aluminium and if you use the wrong sort of electrolyte, the liquid that makes it work, then you have to use virtually pure aluminium, which is very, very expensive. So that just sort of wipes out any cost model and any business model. But so, you know, at MAL, we've developed an electrolyte that just uses ordinary aluminium, and so we get a very, very good cost per mile. If you sort about a vehicle, about half the cost of diesel and petrol. So, you know, we've got a future. So that's been the main barrier.
You mentioned the cost comparison there with conventional petrol and diesel. What about the cost compared with lithium-ion batteries?
So lithium-ion batteries are very expensive to buy, and the amortization cost actually brings that to around about 50 pence a mile if you do the sums. So it's 3 times the cost of driving with diesel or gasoline or petrol. So.
And what are the byproducts from the reaction?
So the byproducts from our reaction are aluminium hydroxide, and this is a benign, safe salt of aluminium, and it's the source of the material to make aluminium in the first place. So we're in a green cycle. So the aluminium hydroxide then gets heated up, turned to aluminium oxide, which is normally mined from bauxite, and aluminium oxide is the stuff that the smelter uses, the aluminium smelter, to make the aluminium in the first place. So we just feed back into that cycle.
And what about, I mean, you mentioned the economics of the technology. What happens if the price of aluminium rises significantly?
So if the price of aluminium rises, the price of the hydroxide rises, and so we're buffered within that kind of differential.
So it's a natural hedge?
Yeah.
That's fascinating. What happens though? Obviously, as the reaction takes place, obviously the aluminium anode will eventually burn out. What happens if I'm on the road at that time? Does the battery retain a level of charge as well?
No, so it's not a charged system. It's more like a fuel. It's like a fuel tank, but the fuel in this case is aluminium. So the accuracy of predicting the end point of when the fuel is burnt out is very high. It's within 1%. So it's just like a fuel gauge. But the range of the vehicle with it is much longer than even with petrol and diesel. So with AI and GPS, you can organise a refuel, which is a 90-second swap in our case. So, you know, we're aiming for that.
Is that something? It's 90 seconds, and is that's something the driver can do themselves? It's just a case of inserting a new aluminium anode, is it?
So the system, if I just show you this,
right.
This is our sort of modular sort of swapping unit, which goes into the back. So this is for a range extender for a Renault Zoe. There are 8 of those in the back, so that it's literally a sort of pull-out, replace into the boot of the car. So this is our first kind of iteration towards full electric propulsion, which is long range.
And you've got an electric van project on which you're working. What's the progress there?
So with that one, we've got 2 apprentices working on that, and we are going to backfill the space that is vacated by the current lead acid batteries. So the vehicle does about 40 miles, and it's got a 40 mph top speed. But with ours, replacing that, the vehicle gets a lot lighter. It's carrying sort of a third of a ton of batteries at the moment. The vehicle's only about 750 kilos. So by replacing the 370 kilos of battery with 60 kilos of ours, it's not just going to go further. We think it's 1,200 miles. It's just going to perform a lot better.
And Trevor, you've got an interesting background. You're ex-Royal Navy and you're also ex-BAE Systems, I think. When did you start getting interested in this technology?
Yeah, so I started at Rolls-Royce. I was a development engineer, so I'm a problem solver. That's my job. Mechanical engineer. I went into the nuclear world straight away. I've been doing that for sort of 30 odd years. Served in the Navy, left there, went into British Aerospace, and I was involved in looking at alternatives to nuclear propulsion because it was so expensive. And one of the alternatives was hydrogen fuel cells. But hydrogen, that was in 99, so I got very interested in that. I left BAE in 99 to form my own company to do hydrogen, but I quickly realised that there's a bit of a logistics problem and also quite a bit of engineering difficulty with hydrogen, and I think that still remains. And along the way I found aluminium air, and I got very interested in that, and I thought, well, actually, that solves most of the problems if you can get that to work economically.
Okay.
So I spent that time on there.
I'm so sorry, I've got to cut you off. It's fascinating talking to you. Hope to see you again. Thank you, sir.
Thank you.
That's it from me. Jane Secker's next.